This is a phone sent by a fan. They said it was damaged by a fall, and though it was repaired, it still doesn't work. The phone contains thousands of dollars in billing data they urgently need. They're hoping our team can try to recover it. When we opened the phone, we saw it had indeed been repaired before. The motherboard shielding cover had been cut off. We connected the power meter for testing. After pressing the power button, we saw current flow, indicating it could turn on, but the screen wasn't displaying anything. This usually indicates a motherboard issue. If it were a screen issue, it probably wouldn't have been sent to us, but we still need to test it with a good screen to be sure. We connected the power meter, pressed the power button again. The good screen also didn't display anything, just as we expected. It's a motherboard problem. We opened the motherboard schematic for analysis. This is the display IC schematic. For the display IC to work, certain conditions need to be met. First is power supply. We can see its input power is VBAT_sys, which is the motherboard's main power. It splits into two paths, one to the backlight boost inductor and another to the display boost inductor. This means the display IC also controls the backlight circuit. Second is the control section. This includes the display backlight enable signal and two LC bus circuits. Below that, there are two bias enable signals. The entire control section directly connects to the CPU. Third is a display boost bootstrap capacitor. When all these conditions are met, the display IC will start working. It then outputs two channels of 5.5V each for display power. With the screen connected, we can measure this at the capacitors below. Switching to the point map, let's check it out. These are the two boost inductors. We need to measure the main supply voltage here. These two capacitors should be plus or minus 5.5V for display output. Okay, we connect the battery. After powering on, we immediately test the sound pressure. The inductor shows a voltage of about 3.6V, but we don't see plus or minus 5.5V on the two capacitors below. This means the display chip isn't working at all. This could be due to a faulty display chip, or it could be a problem with the control section or the bootstrap boost circuit we checked earlier. Alright, we've narrowed down the issue further. We'll remove the motherboard to examine it. Under the microscope, we see the motherboard's inline socket next to the CPU is fully shorted on the MPI bus. Looking at the display section, it has also been repaired. The chip likely has been replaced as well. Some people quietly watch the videos, but secretly like, comment, share, repost, and follow. People like that are just so adorable. We took a confirmed good display chip from an iPhone 16 and installed it. In case the last repair replaced it with a bad chip, we might just get lucky. Okay, we'll reassemble the phone for testing. With the screen and power meter connected, we press the power button. The current indicates it can turn on, but the screen still doesn't display. Looks like our luck ran out. We'll disassemble the motherboard again and remove the display IC once more. Now we'll use a multimeter to test the resistance of the display IC's bottom pins. The control section of the display IC is directly connected to the CPU. After testing resistance, we found an anomaly. One of the pins showed OL, meaning infinite resistance. Checking the schematic, we see it connects directly to the CPU. Double-clicking this disconnected pin takes us to the schematic. The disconnected pin is the third pin on the motherboard. It's labeled as the backlight enable signal from the CPU. Without this signal, the display IC won't work. It seems we'll have to remove the CPU and try to repair the connection with a jumper. We remembered that the display chip from the iPhone 16 has the same function for this pin, so we opened the iPhone 16 schematic. It shows the same third pin, labeled as V_out 1.8V. This means the enable signal is sent from the CPU as a 1.8V high-frequency voltage. If we borrow a 1.8V high-frequency voltage, it might work. Opening the phone schematic, we found a 1.8V power path in the power section. We double-clicked to jump to the point map. All the red-marked areas are part of this 1.8V path. We located the capacitor closest to the display IC and connected a jumper from this capacitor to the disconnected point. Alright, let's get started. We cleaned the pad and connected a jumper wire from the disconnected third pin on the display IC. Secured it with green solder mask. Connected the other end of the jumper to the borrowed voltage point. Secured the jumper with green solder mask again. Okay, the jumper wire is in place. We reinstalled the display IC on the motherboard. Success or failure will be decided now. We reassembled the phone for testing, connected the screen and powered on. Finally, the logo appeared. We disconnected the screen and power, connected the original screen to test it. The original screen wasn't broken. After entering the correct password, we successfully accessed the system. Great, all data has been saved. We removed the motherboard again, reinstalled all parts, then restored the phone to its original state. The fan said they only needed the data, so we didn't test the functions. Our repair task is now fully complete.